Thank you. So I will begin my presentation. So thank you again for
Yes, I can see.
Thank you for coming to this session and inviting me to give a talk here. So I will talk about simultaneous use of CPU and GPU for fast and energy efficient implicit wave simulation. And I'm from Earthquake Research Institute of University of Tokyo. Our target is earthquake simulation. And for example, we need to do some seismic wave propagation analysis or some crustal deformation analysis. And these require solving many cases of high resolution partial differential equation based time history simulations. And in this talk, I will introduce a method that concurrently use CPU and GPU to reduce the time and energy to solution. So as you know, FugakuNEXT will be GPU accelerator based, but also have a CPU, so can be used for both the CPU and GPU. So in this talk, we will target the current generation of NVIDIA GH200 system, where we have a Grace CPU and a Hopper GPU. Okay, so before showing the algorithm itself, I will show some simulation example and why we want to do this kind of simulation. So this one example is solving the underground structure of based on the observation data. So for example, in earthquake simulation, we want to understand the underground structure, which affects the shaking of above ground structures. However, we have only a limited observation at the surface. So we want to estimate underground structure based on the observation data and on the surface. So what we can do is to make many candidate ground structures and then simulate this for ambient ground noise, ground motion. And then we could compare with observed natural frequency of the ground and choose the best structure. In this kind of simulation, we need to do for many ground structures, we need to do many simulations, and this requires a lot of computation. So this one is one example. So we have a ground structure with two layers. One is underground structure is a horizontally stratified ground structure, and one with a circular basin and one with a slanted bedrock. And if we do many cases of simulation, we can compute the natural frequency of the ground, and we can compare this with the observation and select the best matching ground structure, even without seeing underneath, directly observing underneath the ground. To do this kind of many case or large scale simulation in efficient manner, we are now trying to use this data-driven method for solving PDEs. And here we use a predictor to predict the initial solution of implicit solvers in PDE-based time history simulation using data of previous time steps. So if we can predict the solution of the next type step accurately, we can reduce the number of iterative solver iterations, and thus we can enable speed up without the reduction in accuracy. And previously, we've been doing this on the Fugaku system, and we can do this on the for solving this wave propagation system problem, or also apply this for a crustal deformation problem. Okay. So as I have said, we've been doing this on a CPU-only Fugaku system. And also we've been doing this on the GPU-only system, A100 system. And now we can do this using both the CPU and GPU, where we use the data-driven predictor on the memory-rich CPU part, and we use the solver on the high-performance GPU part. So in this talk, I will review the work by Ichimura et al. And SC24 WACC PD paper, and on using this CPU and GPU, and then show the step-by-step implementation procedure in the latter half of this talk. So, okay. So the first half will be the, I will explain the target problem and baseline solver, the proposed method, and some performance measurement results. And the latter half, I will explain the implementation procedure consisting of three steps. First step is the GPU acceleration and multi-core CPU acceleration, and how we do the CPU-GPU overlap. And I will summarize the presentation. Okay, so this is an introduction. So we want to accelerate the PDE-based time evolution simulations using the recent computational capability, which is CPU and GPU. And here we try to use a large CPU memory for storing large-scale data for data-driven methods, and the fast GPUs with lower programming costs. That means we can use some directive-based programming models such as OpenACC, and we can now use this for accelerating a wide range of PDE-based time evolution problems on the GPU. So when we try to use a data-driven methods for acceleration of PDE-based time evolution problems, when we use the CPU, we can use large memory to store the data on the CPU. However, the CPUs are slower than the GPUs. And on the other hand, the memory size of the GPU is small. So often we cannot fit the data-driven method data of past time steps on the GPU. So we need to make the problem size smaller if we want to use the GPU. So we try to use both the CPU and GPUs to solve a larger problem with higher efficiency. So this is the target problem. We solve many cases of PDE-based time evolution problems in a strongly connected CPU-GPU environment. So here we utilize the CPU with large memory and high-performance GPU by fast interconnect between the CPU and GPU by use of the data-driven method. And here we solve a linear equation AX equal F for each time step IT. So here A is a known sparse symmetric positive definite matrix. F is a known input force vector, and X is the output vector. So for a baseline, we use a iterative solver as a big problem size becomes large. And in particular, we use the conjugate gradient method with a compressed row storage for sparse matrix vector product computation. So this is the overview of the proposed concurrent CPU and GPU computing method. So we solve many cases at the same time. So here, this row is indicating the CPU, and this is the GPU. So we solve two sets of problems at the same time. So for this set, we first compute the predictor on the CPU, and after the CPU has done the prediction, we send the predicted result to the solver on the GPU. And then when the solver is finished, we copy the results to the CPU and so forth. And on the other side, we solve another set of problems on the GPU while we do the prediction of the CPU on the other side. And thus we can use both the CPU and GPU at the same time. And here, by using a fast interconnect, we can do this data transfer between the CPU and GPU in a negligible time. So we can use both the CPU and GPU throughout the simulation time. And so these are the details of the proposed concurrent CPU and GPU method. And this is the GPU part. So we can exploit the computing power of the GPU So instead of using the CRS-based matrix product vector, sparse matrix vector product, we can use a matrix-free type sparse matrix vector product. So instead of reading the global matrix from memory, we can compute the element matrix A on the fly. And so we can get higher performance on the GPU because this requires less memory transfer from the global memory when compared to the CRS. This, of course, requires more computation, but on recent GPUs, the computation speed is very high. So by reduction of memory transfer, we can get higher, shorter elapsed time for doing the sparse matrix vector product. Another advantage of using the sparse matrix vector product using a matrix-free method is that we can reduce the memory footprint. And that means we can solve many simulation cases at the same time using this available extra memory. So instead of solving one case at a time, we solve many cases, several cases at a time. So that means this vector X becomes a matrix. And we can use as SPMV with multiple right-hand sides, which are high performance as large random data access is reduced. So this is the details of the CPU part. We accelerate the solver while ensuring accuracy by use of the data-driven method on the CPU. So here we predict the initial solution of the iterative solver as this. So here large X is the data of the previous solutions. So we are now solving for step IT. We store the data of previous S time steps. So this is one step before, and this is S steps before. We also store the data of the previous S time steps to the right-hand side, S. And using this data of large X and large F, the pairs of the previous input and outputs, we can predict the solution of the current step using the input of the current step. And by having a high accuracy initial solution, we could get the reduction in number of solver iteration and shorten the total elapsed time. And since we need to store many time steps S, we store this large X and large F on CPU memory and compute this predictor on the CPU. So this is the more detailed version of the proposed method. We, instead of solving one case at the time on the CPU and GPU, we solve R cases on the CPU and R cases on the GPU each time. So in total, we solve 2 R sets of problems simultaneously, concurrently. And the CPU is used for the data-driven predictor for one set R cases of the problem, and the GPU is used for iterative solver for the other set of R cases of the problem. And data is synchronized before and after the predictor and iterative solver. And we can use the CPU and GPU fully utilized throughout the computation by dynamically changing the number of time steps used in the the predictor. I will explain about the details of this in the later slides. In some problems, we cannot use a matrix-free SPMV, so we can simplify the proposed method such that we use a CRS-based solver and solve only one set of problem on the CPU and GPU at a time. And so in this case, this will be the proposed method with the CRS-based method. Okay, so I will show an example on a numerical experiment on the target problem of a linear dynamic elasticity example. So here, this is the target problem. We are solving for displacement U. And discretization of this problem using a second-order tetrahedral elements and Newmark beta time integration leads to this equation. So this is the sparse matrix, known sparse matrix. This is the unknown vector U, and this is the known vector right-hand side vector. And as a baseline method, we use the conjugate gradient method for using the matrix vector product based on the block CRS format. And the proposed method, we use a multi-vector matrix-free SPMV-based conjugate gradient solver with a data-driven method as an initial solution. And the same preconditioner is used for both the baseline method and the proposed method. And we implement this using OpenACC for the GPU computing part, OpenNP for the CPU part, and MPI for inter-process communication. So first, I will show the performance of the cost-dominant SPMV kernel. And here we measure performance on a single GH200 node, which has a 72-core CPU and one H100 GPU. So here, the memory transfer speed is important. So the map bandwidth is about 10 times on the GPU when compared to the CPU. So here, this is the CRS matrix sparse matrix vector product on the CPU, and this is on the GPU. So we can see that we can get about 10-fold speed up, which corresponds to a 10-fold increase in the memory bandwidth of the GPU. And as you can see, both methods, the CRS is using about 50% of the memory bandwidth, as you can see. So we can get the performance proportional to the hardware memory bandwidth. By using the SPMV with matrix-free method, we can improve the time to solution by 3.7-fold. So here, as you can see, the peak performance is increased, but the memory bandwidth requirement has decreased, leading to higher performance, shorter time on the GPU. And we could also use the multiple right-hand sides. So here we have 4 right-hand sides, and so we can get further improvement in the peak performance, and we can get shorter elapsed time. So here is showing the time per case. So we can get about 1.9-fold speed up per right-hand side from the matrix-free with one right-hand side vector. Okay. Next, I will show the effectiveness of the data-driven method. So this is showing the improvement in the initial solution accuracy. So here, this black circle is showing the initial solution accuracy using a base Adams-Bashford predictor, which is used in the baseline method. So here, we want to solve up to the 10 to the power of -8. So in a standard solver, the initial solution is here. And by using about 150 iterations, we get to the desired accuracy of the iterative solver. By using data-driven predictor, we can get significant improvement in the initial solution. And using the iterative solver, we can get the reduced number of iterations. And these colors are indicating the number of steps used in the predictor. So as you can see, if we increase the number of time steps used for the predictor, we can reduce the number of iterations required in the solver. So this is showing the automatic balancing of the CPU and GPU. So if we use a larger S, that means we could get a higher prediction accuracy, and that means a shorter GPU time. But of course, this requires a longer CPU time for doing the prediction computation. On the other hand, if we use smaller S, we could get a lower prediction accuracy. That means longer GPU time, but the shorter CPU time. So there is a trade-off between the CPU and GPU time. And we can adjust the number of time steps S used for the predictor. So this is showing the time step S for using in the predictor. And by adjusting this dynamically, we can balance the CPU time and GPU time. So here, the blue line is showing the total time, and the orange is showing the GPU time, and the gray is showing the CPU time. And as you can see, the time for the CPU and GPU is almost balanced. And we can see that almost all the time is CPU and GPU is used throughout the simulation time. Also, you can see that the PDE equation, depending on the input data of the PDE simulation, there are differences in the convergence history of the solver. We can adjust this CPU and GPU time dynamically such that we can get the almost same time of the CPU and GPU throughout the simulation. Okay, so this is the total application performance on the single GH200 node. So this is the simulation of the baseline method, CRS-based baseline method on the CPU. So this is only used in CPU. And this is the baseline method on the GPU. So this is accelerated by about 10 times, which is by the tenfold improvement in the GPU memory, hardware GPU memory bandwidth. By using the data-driven predictor, we can improve the iteration, reduce the iterations by about 2.3-fold, and that leads to about 3.3-fold improvement in the time per case. By using the multi-vector matrix-free SPMV kernel, we can accelerate this further and get a total speedup of 86-fold when compared to the CPU-only method. Also, this is showing the power used. So this total module power means this is the power of the whole node, including the CPU and GPU. And the green part is showing the GPU power. So here, we only use the CPU, so the GPU is idle and about 300 watts is used. So if we multiply the time by the watts, we get the total energy usage. By the GPU, when we use a GPU, 600 watts is used on the GPU, and we could get about a 4 to 5-fold improvement in the energy improvement when compared to the CPU-only case. This is, if we use the CPU and GPU together, the GPU is using 600 watts, and about 250 watts is used on the CPU. And so the total watts is increased, but the time is reduced. So we get a reduction about half in the time energy to usage. And by the further improved SPMV kernel, we can get a further improvement in the energy to solution. Okay. So we can use this on a larger system. So we measure this weak scaling on Alps in CSCS at Switzerland. So this machine has many many Alps nodes. Here we measure up to 1,920 Alps nodes. Each of these Alps nodes has 4 GH200 modules, so we can measure up to 7,680 GH200 modules. In the explanation before, I would using only one node, but we can partition the whole FEM mesh into a number of GH200 modules. And we can do the communication of GPU-GPU communication for the solver part is done as a normal FEM program. And the CPU and GPU data transfer is internal to the node. So you can see that only communication is done, internode communication is done by the GPU. So we can get a very good weak scaling, about over 94% weak scaling up to the 7,680 GH200 modules. And we can adjust the parameters of the proposed method such that this is flexible for power caps and varying memory sizes. So on the CSCS Alps system, the CPU and GPU cannot be fully used simultaneously due to the power cap. So in the previous GH200 single node, that one did not have a power cap, so we can use both the CPU and GPU at full power at the same time. However, on this system, there is a power cap of 617 watts per module. So we cannot use the CPU and GPU fully at the same time. So here we adjust the power diverted to the CPU by changing the number of OpenMP CPU threads. So here we adjust the number of CPU threads 36, 24, and 16. So this means that we reduce the power allocated to the CPU when we use a less number of threads. By doing so, we can adjust we can put more power to the GPU, and in this case, we could get about 5% improvement in speed up and energy usage when compared to using 36 threads. Okay, so this is the summary of the proposed algorithm and performance. So we accelerate the PDE-based time evolution problem by concurrent use of CPU and GPU. And this led to the speed up and reduction in energy to solution without the reduction in accuracy. And this is also scalable up to a large scale GPU, CPU systems. Okay, so in the remaining time, I will explain some implementation details. So in fact, this is quite straightforward to implement if you have a GPU-based method already. So we start from flat MPI code, a serial CPU code, and we can accelerate this using a GPU by OpenHCC, etc. And then we accelerate the predictor using the multi-core CPU by OpenMP, and then we enable the CPU and GPU overlap by communicator splitting. And in fact, this step 1 and step 2 is the same in the case without the CPU-GPU overlap. So only the step 3 is new for the CPU-GPU overlap. So this is the acceleration of the solver using a GPU. Our solver is based on a conjugate gradient solver. So this is comprising process local computation and inter-process communication. And the process local computation is the matrix vector products, vector updates, and local inner products. And inter-process communication is point-to-point communications for synchronizing matrix vector products and global inner products. Except for the matrix vector products, the GPU computation is straightforward. And so I will explain about the matrix vector products in the next slide. So this is the matrix vector product kernel. We use an element by element method to reduce the memory reads. So when we do a matrix vector product AP, we load a part of, we do a loop on the element. And for each element, we load the local right-hand side, multiply it to the local matrix, and then map it to the global node number, and then add it to the local, the global vector. So this is the code. This green is the left-hand side. So we initialize it to 0, and then we first generate the element matrix based on some parameters that define the element element property. And then we load the local right-hand side. So this is a mapping, getting a part of the global matrix, which becomes a random cache load. And then we do the local matrix vector product. And then we add this into the global left-hand side vector. So this becomes a random atomic add to the global vector. Okay. So here we do a multiplication of the multiple right-hand side. So for example, we have n-dec multiple right-hand side. So instead of loading one case of P, this becomes a block random cache load. And so the innermost loop becomes consecutive in memory. So this is very efficient loading. And this becomes a small matrix product instead of a matrix vector product. So this becomes also very efficient. And then the addition into the right-hand side, left-hand side vector becomes also a block random access, which is also efficient. So this can be efficiently computed. Also, we only need to generate this local matrix once per NVEC. So this the computation itself is reduced. And next, we accelerate the predictor using multi-core CPU. Prediction computation is partitioned inside each MPI partition. So that means there is no communication between the nodes. And so this computation with OpenMP is very straightforward. Okay. And so this is the last part. We enable a CPU-GPU overlap by communicator splitting. We generate two communicator groups by MPI, split. And we, for the even global ranks, we allocate the group ID 0, and the odd global ranks, we allocate group ID 1. So for example, if we have 4 GH200 nodes, we launch 8 global ranks. And we partition this into 2 groups. And so, and for the local rank ID becomes 0, 1, 2, and 3. Okay. And instead of using the MPI-COM world, we can use the MPI-COM local so that we can use the GPU solver and the CPU predictor using the same code as before. So this is the original code where without the CPU and GPU overlap. So we launch MPI init, read the mesh for the global rank ID, and then compute the predictor, and then use the solver with the MPI-COM world and global rank. So here we rank MPI init to set the global rank ID, and then communicate to MPI-COM split to set the local rank ID and the group ID. So when we read the mesh, instead of reading the global rank ID number mesh, we read the local rank ID. And then in the solver, instead of using the MPI-COM world, we use the MPI-COM local with the local rank ID. And then next, we insert the MPI barriers such that the solver on the GPU and the CPU is synchronized among processes. So here, first for the group ID 0, problem case 0, we first compute the predictor on the CPU. And then the group ID 1 will be waiting until the predictor is finished. When both sets come to the MPI barrier, moves to the next set, and the solver on the GPU and the predictor on the CPU is computed. When both is finished, the MPI barrier is and go to the next session as well. So as you can see, the main part of the code can be used from the normal CPU or GPU computation. Okay, so this is a summary. We accelerated the PDE-based time evolution problem by concurrent use of the CPU and GPU and improved the energy to solution and speed up, and showed the step-by-step implementation using OpenACC, OpenMP, and MPI. So here we use the Gram-Schmidt type predictor, but we can use different type of prediction methods in the data-driven part to improve performance and applicability to wider range of problems. So this is the acknowledgement. We use the Swiss National Supercomputing Center, ALPS, and we thank Hirano-san of NVIDIA for coordination of this collaborative research project. And this was supported by Kakenhi and JST Spring. Okay. Thank you for listening.